Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to share some knowledge that I've never shared with anyone before. It's not that great knowledge because I have much more to share that I won't share with you simply because of the way I've been treated. But I'm going to throw this out to you as a teaser now of what you've been missing out of by letting the bastard scoundrels of mainstream academia, math academia, persecute me the way they have. So this YouTube viewer says, what about the use of differentials with integrals? Example, integral of fx dx. And I said, what about it? There's no problem because dx is a symbolic differential and the integral of fx with respect to dx is a product of arithmetic means. Of course, most mainstream mathematics morons think that that's a Riemann sum. It's got nothing to do with Riemann sums, which are absolute bullshit. Okay, now, and Riemann was an idiot who didn't understand calculus. So I'm going to show you now that separating differentials in calculus means something. But what does it mean? And can you use them like numbers is the question. So when we write integral of fx with respect to dx, we don't care about the area, which is a product of two arithmetic means as derived directly from the mean value theorem in one step. We only care about the primitive function, okay? So how does this actually work? Suppose you have y is equal to x squared. You don't just differentiate each side. You don't just say the differential on this side is dy and 2x dx. This is the way you say it. You say the derivative of y with respect to x is 1 multiplied by the differential, okay? And on the right-hand side, you just have 2x. And now this implies that dy is equal to 2x dx. And this is a perfectly normal algebraic equations where you can separate the differentials because they're exactly numbers or magnitudes, okay? And as I've shown you in my previous videos, if you come back here and you look here where I've revealed what an utter moron Gilbert Strang is from MIT, just go back and look at these videos here, okay? For example, the dick picture with Gilbert Strang. You'll see that differentials are exactly symbolic magnitudes. And so what you can do here in this case, you can say that once you separate these two and say dy is equal to 2x to x, to get back to the original equation, this is what you need to do, okay? Because it concerns area, you need to take the integral of dy from 0 to y. And if you do that, and you do the same to the other side, that's how you arrive back at where you started, okay? So that's something you've never seen. The first thing you've never seen. But I've got a little bit more to show you just for the heck of it, okay? Now, suppose that dy dx is equal to 2x and x is equal to 1. This implies that the derivative at x equals to 1 is 2 over 1 or just 2, okay? Which, by the way, implies that dy is 2 and dx is 1, okay? dy is 2 and dx is 1, okay? So we substitute x is equal to 1 over here, and we see that the meaning of the equation is true, and it can be treated algebraically just like any other equation. So did we have to use 2 and 1? We could have used any other equivalent fraction. Again, look at these videos here on the dick picture and bullshit limit theory, the holy grail of calculus, dy dx, and all these videos that appear after this video here. You can get all of them by going to my YouTube channel and clicking on videos, okay? So let's see again. Suppose that dy dx is equal to 2x and x is equal to a half this time, not 1, okay? In which case, dy will be 1 and dx will be 1, because if you put a half in here, the derivative is 1, which means that dy is 1 or dx, and not or, and dx is 1. And it doesn't matter what you put in here. You could put 15,000 over 15,000 and the equation will still be true, because when you substitute the values back in here, okay, you'll see that the equation holds, all right? Does that make sense? Okay, so in the In both the above examples, we chose the numerators, okay, and denominators for dy and dx. We chose dy is equal to 1 and dx is equal to 1, but as I said, we could have chosen any equivalent fraction. Dy is equal to 15,000 and dx is equal to 15,000. It doesn't matter what you choose because it will still give you a derivative of 1, okay? And they are separable and there are values. They're not infinitesimal bullshit like you hear in calculus mainstream courses, nor like that fucking moron Abraham Robinson with his bullshit non-standard analysis. Okay, it's absolute garbage. Don't even waste your time on that. So for example, suppose we chose dy over dx is equal to 4/2. That means we chose an equivalent fraction here for this particular example 1, right? So when we do that, we have, again, dy is equal to 2x dx. And of course, dy in this case is 4, dx is 2. And again, we have 4 is equal to 4. So once again, the equation is true and can be treated algebraically just like any other equation, as long as dy is proportional to 2 or dy equals to 2 or some equivalent. And dx is proportional to 1 or dx is equal to 1. Okay, so ultimately, it doesn't matter what equivalent fraction you use, you can separate these values, and there are innumerably many. That's why, again, when you get to the dick picture, there is no capital delta x over capital delta y over capital delta x becoming too short, and suddenly, with the use of the hand waving limit bullshit, it suddenly becomes dy over dx. Okay, nonsense. As a final example, let 3y squared is equal to let 3y squared equal to 2x to the power of 4. This implies, and again, you differentiate the left side first with respect to y and multiply it by the derivative, okay? And the right side is differentiable with respect to x, and it's just simply 8x cubed. And so once again, you'll have dy dx is equal to 4/3 x cubed over y. But from this equation here, y is equal to the square root of 2x4 over 3. Therefore, dy is equal to this coefficient here times dx, okay? So if x is equal to 1, then dy over dx is equal to 4/3 over the square root of 2/3. And so dy is proportional to 4/3, and dx is proportional to the square root of 2/3, or equal, doesn't matter, okay? Resulting in resulting in this equation here, if we substitute the values in, so we substitute dy, this dy here, this dy 4/3, okay, and the dx, and of course x is 1, and so we have 4/3 is equal to 4/3, as expected. I didn't put the value of x in here as 1, but that's what was chosen right here, okay? So you choose different functions and several equivalent forms for the derivative to convince yourself of the truth that differentials act and are treated exactly like numbers in equations. Therefore, dy and dx are separable, and there's no bullshit a la Gilbert Strang from MIT, such as the limit of capital delta y to delta x as delta x approaches 0 becomes dy dx. This is just total nonsense. So, and I do know better. So don't write in the comment section that you know better than me. You don't. You're a moron. There is no such thing as an infinitesimal. It always was a bullshit concept and always will be. It was invented by the likes of Newton and Leibniz because these two clowns were trying to outperform each other, when in actual fact neither of them had any clue why their methods worked. In the new calculus, differentials are very well defined and correspond exactly to the finite difference quotient. That is, you can say that dy is equal to the numerator and dx is equal to the denominator. Using the garbage approach of the calculus fathers, Newton and Leibniz, dy is not equal to f of x plus h minus f of x, and dx is not equal to h, except in one special case where f is a straight line. But we all know that straight lines all have slopes, as rise over run, don't we? You can learn about the first rigorous formulation of calculus in human history at this link, okay? And you can also see how I fixed your bullshit mainstream formulation at this link, okay? The Holy Grail was realized, this Holy Grail was realized from my historic geometric theorem of January 2020. And this is a link to it so that you can study it. Now, become a follower of me on academia so that you can have access to updates. For example, I might decide later on to put a little dialogue with Claude's, the most advanced chatbot, which is Anthropic's Claude 3, and convince it of the facts that are in this article and show you how it will be convinced, because what I'm telling you is the truth, it's fact, and it can't be refuted by any moron of mainstream mathematics academia who don't know these things, who can't teach you these things because they don't know them. So if you're not already a subscriber on my YouTube channel, this channel here, become a subscriber. Click like, tell your friends about it. Remember to click like and tell your friends about it. Tell your teachers, tell everyone you know, okay? And seeing that I've given you new knowledge here, take the time to reach deep into your pockets and donate, okay? Because nobody else is giving you this, and I'm giving it to you for free. And I'm not telling you to donate if you can't, only if you can, right? So, in other words, I know it's really hard out there. You're going through rough economic times, but you can donate at this link. And because academia.edu has disabled links, you can actually find a place to donate on academia.edu simply by going to academia and clicking on my profile. Okay, on my profile here, and you can come down here, click here, and there are two places you can donate here at GoFundMe and also at another one in the detail section. So that's pretty much all I have to say. My name is John Gabriel. This is New Calculus Channel. Till next time, goodbye.